This is how I'd use the simulation in front of a class to explain the relationship between charge and current. Depending on the class, I'd probably use a series of questions like this. What's this a picture of? It's a circuit diagram with wires, battery and bulb. What do the black dots represent? They're electric charges. It's worthwhile keeping the word electric. In our simulations, we show conventional current, so each black dot represents 1 coulomb of positive electric charge. For the moment, charge or even electron is fine, but more able students might clock they're going the wrong way for electrons. Well, what are the charges doing? They're just jiggling about. Where are they going? They're not going anywhere. How could we make them start to move? Well, we could increase the battery voltage. The charges are part of the atoms that make up the metal wires, and so they're already there everywhere in the circuit. The charges don't come from the power supply, that just sets them in motion. So let's do that now by increasing the voltage of the power supply gradually, and watch what happens to the charges. So here are some questions. Where do the charges start to move first? Everywhere at the same time. How quickly do they move? Well, they move pretty slowly. Do you think the bulb would be on or off? It should be on or maybe dim. And how quickly will the bulb come on? Straight away. Why does the bulb come on straight away? Because the charges start moving everywhere in the circuit at the same time. These two ideas, that the charges are already there everywhere in the circuit and they all start moving everywhere at the same time, are crucial for having an accurate mental model of electric current. It's these two facts that explain why a light bulb comes on as soon as you flick the switch. I think it's also important to emphasize that the charges happen to move very slowly along the wire, much slower than a snail, but the charges don't need to move fast for the switch to work quickly. A common misconception is that the wires start empty and that the battery provides the charges, which move very quickly through the empty wires, and that's how they account for bulbs coming on straight away. So what's this movement of electric charges called? It's an electric current. What happens to the size of the current as I increase the voltage? Let's see. The current gets bigger. And how can we tell this from our simulation? The black dots move quicker. The size of an electric current is related to, but isn't exactly the same as, how fast the charges are moving around the circuit. The size of the current is how many coulombs of charge pass a point in the circuit each second. And this depends on how fast the charges move, how closely packed the charges are, and how thick the wire is. So where is the current biggest? Nowhere. The current is the same everywhere around the circuit. And you can tell this because the charges are all moving at the same speed everywhere around the circuit. And what would happen if the current was different in different parts? Well, the charges would keep bunching up in some places and spreading out in others. Just like a queue of people, charges like to keep a fairly fixed distance from each other as they move, and this is because the electrons move through a fixed lattice of positive ions. They can't bunch up too much because they repel each other, and if they spread out too much, they'd leave regions of net positive charge, which would attract them back to fill it.